wait a little bit.
Will now be recorded.
Looks like we are fewer than usual, so we are around 45 in this moment. Sorry, let's wait a few minutes as usual. So here in Italy, things are getting better. From since the 3rd June, we can circulate also freely in the other regions. I hope also in your geographies things are a little better now, also for business, of course. I guess maybe the lower number of attendees is explained by the fact that many people are on the installations or in office having to run the business. Probably this explains the lower participation, but no problem. All the webinars are recorded, so you will be able to follow the webinars in any moment and send us your questions also after watching the webinar anytime. Just another 30 seconds and we start. Okay, Stefan, I think we can start now. So welcome everybody. Welcome to this 6th webinar of our long journey through the IME offer. So today we will explain in detail our range of low voltage transformers. Stefano will go in deep on all kind of models and also he will add some examples on how to choose the right transformer and also several tips. So let's go, Stefano, with the following slide. So as usual, Matteo speaking, export manager, with Stefano, who is the technical expert doing all the explanation. Paolo and Maurizio are connected. As usual, they are available to answer live to your questions on the chat. Feel free in any moment to place your questions in the chat. Now we are 62, very good, we are increasing the number. Go, please, Stefano. So the agenda of today, first of all, a quick introduction, then Stefano will go in deep in the explanation of what are transformers, really starting from the basic theory, let's say the principle that are under the way transformer work. And why also we use transformers, and you will discover then our huge range of low voltage transformers. Then, as I said, some application examples, several tips, and at the end of the webinar, as usual, we'll dedicate several minutes to answer to your questions. Okay, let's recap a little bit the journey, because this is the 6th webinar. Then we will have another one in 1 week on Earth leakage relay. So let's see what were the steps of this journey. We started with energy meters, in particular with the new range of energy meters that we have just launched a few weeks ago. Then we entered in deep in the multifunction meter range. On the 3rd webinar, we examined in detail the one model inside the multifunction meters, which is the NEMO 96EA, because it's, let's say, a first step in the power quality, which is another chapter of the electric measurement. Then we went more on the software side, so on the software solution side. We discovered all the features of our web server. Our web server is in continued evolution. Probably many of you already received the new firmware of the version 3.8.1. The version 3.8.1 with many new features will be available, downloadable from the website, IME website, starting from 9th June. After the web server, we explained the NEMO SX range, which is, let's say, quite strictly connected to the web server, because it makes possible also the automation of the electrical cabinet with its automation control modules, also its alarm modules, etc. So it's a very interesting system that we encourage you to try and to test. As I underlined several times, for both in the webinar of the web server and of the NEMO SX, it's very important to target right customer prescription. Don't focus just on panel builders, electricians, and electrical distributors. Today, as I said, we are discovering our whole range of low voltage transformers, and in the last webinar we will conclude with the earth leakage relay range, which is also a very important range because we speak about protection. Said this, I just want to add another point that I will also repeat in the last webinar. We will do a test after the last webinar. We will send a test and with an evaluation, because we would like to give certificates to the people that attended the webinars that show us that they know how our products work. So prepare yourself for the test. If you need, see again the recorded webinars, the previous webinars. After the last webinar, as I repeat, you will receive a very interesting test. It will not be extremely high level of difficulty, but it will not be simple either. So prepare yourself. Okay, Stefan.
Okay, thanks, Matteo. Hello and welcome to our 6th webinar. As already said by Matteo, I'm Stefano Chiarichini, Technical Commercial for the export part of the IME brand. Today I will introduce to you our range of transformer. So, when taking industrial electrical measurement, they are the first link in the measurement chain. Current transformer make it possible to work back to the previous current value applied to the primary through the measurement of the secondary current. They are used from the simplest application with analogic indicator to the most complex where to use a transducer, energy meter, or multifunction is contemplated, and finally is monitoring system. But let's start a little from the base. Let's start by introducing what is a transformer. The transformer is a static electric machine powered by alternating current based on the phenomenon of the electric induction, intended to transform the voltage and the current factory of electric power between the primary circuit input and the secondary circuit, the output of the transformer. They make wiring easier and cheaper and allow to use standard meters and relays that do not have to be designed for high currents or voltages. So also a reduction of cost of the measuring instrument. An electric current transformer in the primary winding generates a variable magnetic flux in the transformer core and consequently a variable magnetic field through the secondary winding for Faraday law and the Lenz law. This variable magnetic field induces an electromotive force or voltage in the secondary voltage winding. This effect is called mutual induction. The transformer is a machine capable of operating essentially in alternating current because it generally uses the principle of electromagnetism linked to the variable's flow. The efficiency of the transformer is very high and the losses are very low. In iron, due to the effect to the hysteresis and the eddy current, and in the copper due to the Joule effect. If an electrical load is connected to the secondary winding, an electric current flow through the energy through the transformer is transferred from the primary circuit to the load. In an ideal transformer, the voltage induced in the secondary winding is proportional to the primary voltage, Vp. And this is given by the ratio between the number of the turn in the primary winding, Np, and the number of the turn to the secondary winding, Ns, like in this formula. So, in the vast majority of the transformer, the windings are located around the ferromagnetic core, as shown in the figure. And just what is shown in the figure is what is used in IME to create the voltage transformer. While for the current one, well, we will see that there are various types of current transformer in the shape of toroids that can be open or so-called with primary winding. As for those with the toroid or open core, same as first, but openable core, the operation principle remains the same as the seen a little while ago, because it uses the magnetic field generated by the current passing through the hollow core. This cable brings the power to the connected load. Coils capture this current flow generated by the magnetic field and return it to the secondary side to a current value proportional that the flow of the primary. This ratio, as I say, is given by the number of windings made of the transformer core. Does anything change for this winding primary? Well, mostly nothing. We find on the left the closed core current transformer model. On the right, however, the primary winding transformer, where in practice the primary cable winds around the magnetic core in which of the secondary coils is also present. The rules seen above remain the same. Same goes for the windings ratio to understand what is the CT ratio. So let's go starting right from the current transformer, which I will now call it CT. Well, the IME brands offer a complete range of voltage, of current transformer regulated in terms of measurement and protection, scrupulously compliant with the national and international standard. The ESC 61869 and EN61869. The parameter 1.2 and 1.2 for the 2.1. These standards provide for general and additional requirements for inductive transformer. These provide the concern, the condition of the service, the nominal quantities, the design and the construction, the evidence and the security, and the classed and errors. Our current transformers are used to measure current up to 10 kiloamps. As we will see, there are three types of transformer: measurement, accuracy, and protection. And for all, we have a reference and isolation voltage of 0.723 kilovolts, and for a special execution, we also reach 1.26 kilovolts. We begin to see the measurement CTs, in particular those intended for low currents, the primary wound CT. In the aim range, we have a primary CT wrapped to measure current ranging from 1 to 600 amps, with different performance and accuracy class. They are generally chosen to measure low currents up to 50 amps and maintain a good level of precision. This is because the magnetic field generated by these currents does not allow to have an accuracy such as to reported on the secondary side of measure it. Above 50 ampere, we can use the passing cable or busbar CTs. Here we find a range capable of measuring currents ranging from 40 to 10 kiloamps. We find in the catalog a vastness of CTs with different window performance and measurement classes. As indicated, they are ideal for 50 amps current and all type of circuit. This is because having different cables or busbars in the world, there is need for different all. For the cable side, we have a window from 25 mm to 110 mm. For the busbar side, we have a window of 16 to 20 mm window at 120 for 255 mm. But be careful. Obviously, where a busbar passes, cables can well pass through it too. Well, we see in this example also cable pass through a busbar current transformer. Well, in the last webinar was about supervision. We have introduced the revamping concept. And if the NEMO 6 is an excellent solution for the revamping, what is the first step to measure? Current transformer with openable core. The range starts measuring currents from 60 amps to 5 kiloamps, always with different performance classes and window. As I say, they are ideal for installation on existing system because they do not interrupt the primary side of the circuit or modify it. Again, different circuit, different window. For the cable side, we go from 110 at 10 mm to 150 mm. For the bus side, we go from 20 for 30 mm to 80 to 160 mm. The same concept remains for use cable for busbar CTs. Well, we are talking about measurement CTs. The EN61869 1.2 provide that a CT is in class 0.5 or class 1 must be tested from 5% to 120% of the rated current and must follow a ratio and angle error as shown in the figure. Note that the closer you get to the rated current, the smaller error will be. For class 3 CT instead, tests are performed from 50% to 100%, 120%, sorry. This is a big limitation. That's why I suggest using a primary CT, winding primary CT, up to 50 amps, and beyond use the passing cable. In fact, the smaller passing cable called TABB will be in class 1 starting from 50 amps. Well, what if I want to have a precision and at the beginning of the scale? Well, we can help us with the accuracy CT. The range is capable of measuring currents from 5 amps to 150 amps using the primary winding, and from 150 amps to 4 kiloamps via passing cable. Here we will find the classes of 0.2s, 0.2, 0.5s, and are generally used in situations where better precision and strong current excursion are required, such as in the laboratory test. As I say, precision CTs can increase the level of the precision and widen the measurement range. In fact, for the class 0.2s and 0.5s, in this range goes from 1% to 120%, while for the class 0.2 remain the same of the class 0.5 or 1%, but improves the ratio and the angle error. Well, instead, if I have a strong current surges, controlled or not controlled, that I need to measure, I will use a protection CTs. Here too we find a breakdown by type, from 5 to 600 amps for the primary winding, and from 250 amps to 80 kiloamps for the passing cable. Here the standard indicate the classes in 5P, 5P5, 5P10, 5P15, and 5P20, where the first digit indicates the error in percentage, so 5%. The second letter indicates that is a protection transformer. The last digits indicate how many times the nominal current can be higher without going into saturation. As I say, they are used in combination with relays and instruments that must withstand high current peaks like engines. Here too we find an error deriving from the transformation as visible in this table. So, a sure mention goes to the summation CTs. These CTs are able to sum up to 6 different measuring points. The range has 3 models with different performance and accuracy classes. As I say, they are used when I can only install one measuring instrument, but I have, for example, 2 separate loads. The function is very, very simple. Take, for example, a company where I want to monitor the consumption of 3-phase load in a single measuring instrument, but they are far away apart. Well, I install 1 CTs for each phases for a total of 9 CT. I sum the respective phase with 1 summation CTs. So I take the first R, which has installed the TA 100/5 amps. The second phase R with installed another TA with 200 amps of ratio /5, and the third phase which installed the TA 300/5 amps. I do the same for the S and the T. So I connect the 3 summing CTs to the measurement instrument, set the current transformer ratio of the sum of the 3 CTs. As an example, I sum the 100, 200 plus 300, it is 600. Divided by 5, I have to put on the instrument 120 as a current transformer ratio. Well, let's continue with the voltage transformer that I will call from now VT. As for the current one, IME offers a complete range compliant with the national and international standard, the AN 61869 1.3. IME VTs are low voltage transformer up to 1 kilovolts, And as for the CTs, they are divided into 3 categories: measurement, accuracy, and precision and protection. Sorry. Here, these installation references are obviously based on the voltage of the primary site. Up to 600 voltage, we have 0.723 kilovolt, and beyond this, from 600 volt, we have insulation 1.26 kilovolt. IME measuring VTs are used for the voltage from 100 volt to 1 kilovolt, ideal for measuring both phase and neutral phase voltage. As for the CT, the IME range is characterized by a wide range of code that different in performance and measurement class. In addition, the measurement VTs can also be used for protection. In fact, on the labels, we will find the double class 0.5 or 1 and 3P. The principle of the classes remain the same for the CT. And also for the VC, we find the precision range capable of measuring voltage from 230 volt to 1 kilovolt in class 0.2, ideal for very precise measurement where required, like, for example, testing lab. Well, after this introduction to our range, how can I choose a correct CT or VT? Let's start from the CT. We have 4 parameters to keep in mind: system rated current, busbar or cable size, measurement class, and performance. So, start with the first one, the system rated current. This is used to determine obviously the transformer primary current. Do not take one of the errors is to take the nominal value of the circuit breaker as a reference, because a lot of time it's always oversighted. It's important to take the real consumption of the various values. This is an example. I have a breaker of 800 kilowatt, the voltage of 400 volt. But I have a 5 load of 16 kilowatt each one, and a power factor of 0.95. So I take the power of one load, 600 kilowatt. I divided it by 400 for the 163, the radius of 3, and for 0.95. It gives me the currents for one load, 91, more or less 91 amps. I multiplied it for the quantity of load, 5. I found that my real consumption is more or less 455 amps. So I'm going to take a primary of 500 amps, so the nearest of the maximum current flow in this circuit. The second step is how big is the hole, the window we have to choose. This is make it possible to choose a CT windows that is large enough to pass the phase or bus bar through it. Always choose a slightly bigger windows as to have a little play to use during installation. If I take it is so tight, I can't insert the right cable, and it make a very troubling installation. Here is some example. I have a cord, a cable of 120 square millimeter. So we find for the installation of the cable manager, that you find a table that for the 120 square millimeter, the diameter is 22.4 maximum diameter. So here I chose a model, as I say, a little bigger than 24.3. In our range, we have a CT, sorry, called TH327, with a window of 227. So the other step is to know what type of measure I have to do. So you have to select my measurement class. If I choose a measurement class 0.5 or 1, is recommended for measuring power, electricity, and power factor or cost phi. For the class 3 is used for the current measurement or a meter like an analogic one. If I need a more accuracy measure, I have to choose a 0.2, 0.5s or 0.2s current transformer. If I need to protect my line, my circuit, I use a protection current transformer in 5P class. Here an example. If I have a panel with a low level load, I can go to select CTs in class 0.5 or 1. If I have a panel that I need a high accuracy, I'm going to select a current transformer in class 0.2, 0.2s, and etc. The first step is to choose the performance or the maximum rated burden that can generated by the current transformer. This represents the maximum load that can be connected to the secondary terminal of the current transformer. This load consists of the self-consumption of the instrument, so the measurement instrument, that is normally more or less 1 volt amps, plus the absorption of the cables connecting from the CTs to the instrument. This latter depends on the length of the cross-section of the cable. So you can find this practically table that you find what is the absorption with different cross-section of the copper cable. So I take an example that mesh up the previous example. I have a breaker 800 kilowatt that we say we don't take in charge. We have a voltage of 400 volt, the loads of the 5 load of 60 kilovolts, and the power factor of 0.95. The cord of the 120 square millimeter, and a class, and I need a minimum of class 1 because I need to have a measure class with a low level load, for example. So I select, as you say, a CT, sorry, called TA327, the right call, with the ratio 500 to 5 amp. So my question is, can I use this current transformer if I have 40 meters from the cable to my instrument? So I have to make some measure. So I take the performance indicated in technical note, this one. As shown in the figure, I have for the class 0.5, 12 volt amps. For class 1, 50 volt amps. I take the last table. As indicated, I have different cross-section for the connection from the instrument to a current transformer. I take, for example, a 2.5 square millimeter in class 0.5. I take, for example, the class 0.5. So 12 volt amps. I have to reduce to the sum, the measure instrument consumption that I see is more or less 1 volt amps, and divide it for 0.41. So I go from the instrument to the current transformer up to more or less 26 meters. So yes, I can use this. If I use 1 square millimeter in class 0.5, I have to take the performance of 20 volts, and I remove the measurement instrument consumption that I say is more or less 1 volt amps, divided by 1, and I have more or less the distance of 11 meter, so I can't use 1 millimeter. So, but if I use a square millimeter in class 1, so 50 volt amps, I remove the measurement instrument consumption of 1 milliamps divided by 1, the absorption of the 1 millimeter cross-section copper, I arrive to the 40 meter, so I have really in borderline. So let's take this example of borderline. So if I use this 1 millimeter in class 1, remember the table of the calculation performed so far concerned to the secondary of 5 amps. But as is visible in the right column, using the same cross-section for the CTs with the secondary 1 amps, it absorbs 25 times less than 5 amps CTs. So by using a CTs with the secondary 1 amps, I can reduce the section of the secondary cable and therefore reduce the installation cost. The example above become this. So if I have 1 milliamps, I use a 1 amps of the secondary, so I have divided this performance by 0.04. I can go far away up to 300 milliamps. But be careful. Remember the table previously seen and on error in the class. By law, these values are valid by the standard of the AEN. These values are valid if we use a performance ranging from 25 to 100% for class 0.5 and 1. While for the class 3, you need to use from 50% to 100% of the performance. So be careful to choose a too performing CT. Well, and how I choose the right voltage transformer? The criteria remains the same without, of course, the cable section. Then the system rated voltage, the measurement class, the performance, and the security. This is used to determine the transformer primary voltage that take the excess voltage or close as possible. So you have to chase the system rated voltage that closest of the system rated voltage. This is an example. If I have a rated voltage of 690 volt, I have to select a primary of 690 volt. If I have classes 0.5 recommended for measurement power electricity and cost fee and whatever for the class 3P for the protection system. This is an example with the panel with low level load. I use a measurement VTs in class 0.5 or 1. With panel with high accuracy, I'm going to use VTs in class 0.2. For the performance, this represents the maximum load that can be connected to the secondary window of the VTs. Respect to the CTs, the load consists only of the self-consumption of the measurer's instrument, so not also the cable. For the security part, many panel builders don't want to have, for example, the 400 volt into the cabin, into the panel. Furthermore, the VTs can be further protect the instrument from any other spike that spill on the voltage side. Special mention goes to the Riccati coil. Because as already seen in the previous NEMO multifunction webinar. First of all, it is certainly an excellent alternative to the classic current transformer, but it cannot be installed anywhere. The coil does not have a ferromagnetic core like the CTs, but has air. It is a very flexible and can be opened, and these are essentially the most two important strengths, as I said. They suffer in system where there is a strong harmonic component. This unfortunately generate a bad measure for which it is always however to have a minimum knowledge of the system before choosing the solution. Another things, based on how you set the operation range, you have 3 step, 1000, 3000 and 5000. The coil will start measuring from 2% of the full scale. So this is to tell you that the currents below the 20 amps, it will be better to give on the classic current 3C with C below. Riccati coil are sold in kits with the NEMO 96 HDLE and D4LE. For those who have missed it, they will find a link in the email post-webinar to go and review that course. Until now, we have talked about alternative current, but for direct current, in IME we have a range of shunt. This gives a signal in millivolt directly proportional to the measurement current. They are able to measure current from 30 amps to 6,000 amps in class 0.5. We will find a different code for the various primary currents, just like the CTs. Being a totally copper, the dimension will be vary as the primary current increase. Okay, we have come to the end, but first I would like to leave you some suggestions and tips for installing the transformer in practice the current transformer. Let's start with the installation. Unfortunately, it is very common to find an assembly and wiring error in the installation, even if installation is very simple. Starting from the most common passing cable or alternatively the open core, the concept is the same. The cable or bar passed through the CT respecting the direction of the current. In CT there are two phases, primary called P1 and the secondary called P2. The currents enter into P1, therefore P1 must look towards the energy source and exit in P2, therefore P2 must look towards the load. To help us, our CTs, there is an arrow visible in the image next to the CT. The secondary, on the other hand, must follow the wiring diagram issued by the manufacturer of the measurement instrument. For SCTs with the wired primary, the concept is the same, but in this case, the cable that goes to the load must be interrupted and connected to the current transformer, always inside P1, and resumed on the primary side P2. In case of wrong polarity of the primary or the secondary side, I will return an error of measurement, mainly on power and power factor. I remember that the current is a vector which is multiplied with the voltage vector, generate a power vector. Therefore, if the current vector has an inverted sense, the power will have a negative or a positive sign, depends on whatever you are producing or consuming. Another tip, it's about the connection and security. If a secondary cable is disconnected, a dangerous voltage could be generated which could damage the current transformer itself or the operator who is working on it. For this reason, it is essential to check the connection and in case of maintenance, short-circuit the current transformer secondary. IME has an accessory in the catalog that performs this operation automatically, shorting the secondary in open or if it open, or restored in the standard condition. Well, last tip, or better, a personal selection. As I say, when choosing a current transformer, it's highly recommended to choose the CTs based on the real consumption of the machinery and not on the basis of the nominal value of the circuit breaker. This is because, in fact, many times this is oversighted. What does this mean? If I choose a current transformer, for example, 300 to 5 amps, and the real current is 10 amps, for class 0.5 or class 1, is it in class from 5%, therefore 15 amps. The current transformer will be working out of class, giving a strong angle error. That is reported on power values, consequently on the measured energy. Unfortunately, I have seen many installations in this condition, and where it's possible, we can take advantages for this trick. Let's just take a current transformer of 300 amps to 5 amps. We can decrease the ratio by making a multiple loops of the primary cable on the CT itself. By doing 3 loops, we will get a CT with 100 to 5 amps ratio. So 5% is 5 amps. So we are in class. Okay, that's all for today. I hope I have not upset the ideas about the CTs and their choice. Here I leave you the references for the brochure, the technical note, and an excellent white paper prepared by my colleague Paolo Meloni, in which you will find another insight and example of the choice of the transformer. So, it's finished.
Okay, Stefano, let's see some of the questions that Stefano, sei muto. You are
okay.
muto. Let's see some of the questions that our attendees have placed. So the first one for Hugo, it's more related to information. So Hugo wanted to know what about the DWG files or 3D files. We answered him that this should be treated in a dedicated, in a private mail exchange, let's say.
Okay.
Then there was a question from Beat asking, are CTs and VTs suitable to use on a secondary side of a frequency converter, for instance, from 20 to 400 Hertz? And more in detail, the question is,
the working frequency for the current transformer. What is the working frequency for the current transformer, more or less?
But basically, the question is, are CTs also suitable for 20 Hertz?
Yes, yes. So what is the range of frequency how they work? So the normal current transformer, the standard current transformer work from 42 to 72 Hertz. We have a special execution for 380 Hertz to 480 Hertz. So it's only working in these two range, not from 20 Hertz up to 100 Hertz. You can use this, but they are out of class. That's because when you increase the frequency, it increases also the performance. Because if you increase this frequency, the magnetic field increase this is power, and you can the windings are able to taking this magnetic field and have a better vector of current. So you can use it, but they are out of the norm class.
Okay. From Ivan, why are there two classes in characteristics of the CT? For example, 0.5 and 1, and not just one class?
So because that you find in the example, when you exceed the performance of the class 0.5, you are going to class 1. So you find two classes because you have a performance on the current transformer. when you reach the maximum values of volt amps of a class 0 to 5, as we see in the last example, for example, I retake this example, when, or better, the table of the TA327, this one, okay. When I reach the 12 volt amps, in this example 20 amps in class 0.5, and I exceed these values, I go to another class. I pass from class 0.5 to class 1. So it changed the error, the accuracy of the current transformer up to 50 amps. Over 50 amps, you are into another class. In this example, there isn't assigned the volt amps in class 3 because it's not tested for class 3. So you increase the error if you exceed the maximum performance given by the current transformer.
From Marco, what is the minimum current percentage that that I can measure with ICT?
What is the maximum?
Minimum current percentage that I can measure with ICT.
So the norm say for the precision sorry, for the measure current transformer is the 5% of the nominal current. For the accuracy is 1%. That does not mean that before the 5% or the 1% you don't measure nothing. You measure from more or less 20 milliamps of the current, but they are out of class. They increase the error, the angle error. So the vector of the current is not correctly reported to the secondary. So it measures, but out of class with the high error.
From Lawrence, why does secondary current fluctuate so much sometimes? For example, from 0.8 ampere to 5 ampere. Is it because it is low quality or insufficient VA, or because of oversized CT?
Both. As we say, we have 4 steps to choose this. If I exceed the performance, I have a lot of error on it. If I go in low rated burden, so as we say in the last table, if I go under the 25%, under 25% of the rated burden user, I have a bad measurement. And other things, in many wiring diagram, you find that you have to connect the earth on the secondary of the current transformer. If I have a bad isolation earth, this isolation can modify or can make a bad measure, a bad report of the vector of the current.
Okay. Now, Marco, how works the syllable terminal cover at a COP?
How? Sorry?
How works the syllable terminal cover, the ATA-COP range?
Oh, okay, the syllable cover are only that you find in this photo. I'll try to take another photo bigger. This one, for example. This one. The syllable are these two. Try to this. Okay, these two plastic cover. You have only to take to buy this one and put on the secondary of the current transformer or the voltage transformer. This is the the copper for the data cop for the voltage transformer. You have only to put on this, and with the C-label, help Matteo, what is the C-label link for what do you say for sealed the current transformer with an iron cable or the plastic one. You have only to buy it and put on the secondary, nothing else.
Okay, from Hussam, it is linked, I think, to the question from Bert. Is it available for 50 Hertz also?
50 for what is?
Frequency 50 Hertz, I think. I understand this.
50 Hertz, yes, is standard one. As I say,
Okay.
from 42 to 58. So it's standard one.
Okay, question from Rajesh. Why selecting CT in connection with our NEMO meters? CT ratio between 50 to 80 ampere, then secondary 5 ampere or 1 ampere. Meter is class 1 for energy. In order to have good results, which class of CT would be ideal to get accurate readings in NEMO meters? Is there a selection guide provided?
Sorry, the last phrase is?
Is there a selection guide provided?
Yes, you find in this slide after a webinar. I sent this presentation, and you find all the example. Also, at the end of the link, you find other example how to choose the current transformer made by Paolo Meloni.
Okay. Several questions from Hussam. If I have 1000 or 1500, 2000 kVA, what is the required class for the CT?
Depend of type of the measurement you need. If you need to only take under control the current with an analogic instrument, you can go on class 3 current transformer. But with these high values of power, surely you find a class 1 or class 0.5 current transformer, depending of the performance, depending of what you connect on the secondary of the current transformer.
Okay. Janne, is 100 ampere CT lowest in class 0.2S?
100
ampere.
Okay, no, we start our range from 250 amps. That's why, as I say, the rule, or better, because the current transformer, or better, yes, with the primary winding. With the primary winding, you find the transformer, the accuracy transformer in for 100 end. If you want, is meaning right, you want a current transformer with passing cable, you can't use this one because the magnetic field generated by 100 amps is not enough to have this type of accuracy. You have to use the winding primary that you see in this slide. Measure, passing cable, open core, and accuracy. You have to winding primary from 5 to 150 amps. So you have to use the winding primary. With the winding primary, yes, you can use, you have a class 0.2.
Okay. Lawrence, is it necessary to connect CT to Earth? I always see that on Siemens datasheet, but in practice, very few operators do that.
Okay, depend, because in a lot of our datasheet, the Earth is, as you say, Matteo, tratteggiata?
Dotted.
Is dotted because it is not necessary, because depend of the measurement instrument. If the measurement instrument need the Earth, you have to connect it. So depended not on the current transformer, but depend of the measurement instrument, the wiring diagram of the measurement instrument.
Dina, does fluctuating rating power factor, example 0.75, have much effect on the accuracy of the CT?
No. As I say, in the current transformer take the vector current from the primary and report it to the secondary as it is. So it doesn't change the vector. You have an error of this cable, but it depends of the ratio, the current transformer ratio nearest the maximum current flow on the primary bar or cable.
Boris, don't you take a risk if you select a lower current ratio for the CT compared to the breaker values? If you saturate the CT, if you change loads after a time, the change of CT might not have been documented, but the breaker is.
Okay, yes, is right, but if you change your system, you know that you have also a measurement system, so you have to use, you have to modify also your measurement system. That's why you, for example, use the open current transformer. As I say, is not it's not good to take the breaker values, because the current transformer are tested, are in class, for example, for a measure class from 5%. So if I have a breaker of 100 amps, I speak in amps, but normally I are in power. For example, if I have 100 amps, and my real current of my system is 50 amps, or better, 30 amps, I am lower the 5%, so I am out of class. That's why it's more important to use the real current transformer, the real current flow in my circuit, and not the breaker, because I lost a lot of accuracy on the of the beginning scale of the measurement for the first current.
Boris, when would the CT be saturated above 120%?
So depend of type of current transformer. In every current transformer, you find what is the saturation percentage. For example, for the low current, for example, up to 500 amps, the saturation is more or less 120. For the models up to 500 amps, the saturation is 100%. So the nominal current.
No more. Sorry, can you repeat the last thing? Sorry.
So it depends of the model you choose.
Okay. No more questions now. Let's wait a few seconds. If no question arrive, we go on and conclude.
Poi l'ho verificato a volta, lo dobbiamo vedere.
Feel free to place your questions or now, no problem. We have a few minutes. It's 5 past 12. But it looks like we have no more questions, Stefano. So we can conclude.
Okay.
Grazie.
Just go to the last slide.
Okay. BTs, Riccati Coil can transform.
Okay. So as Stefano said, you will receive as usual an email with our survey and all of the related attachment of this webinar about low voltage transformers. As Stefano said, you will find a very useful white paper about transformers. See you in 1 week, same time, same day, same time, to see the webinar, to watch the webinar of earth leakage relays and protection. As I said at the beginning, after the last webinar, we will send you a test because we want to see if our webinars were effective on your knowledge. And based on the test result, you will receive a certification of trained, let's say, trained participants. So thanks again, really, for your participation. It's always a pleasure. See you next week. Goodbye.
Thank you.
Thank you. Goodbye.